Hi guys, welcome back to the channel. In this video I'll be looking into Kw, Ka and pKa and doing some calculations with those from the acid and bases topic in the A-level chemistry curriculum. So let's begin. Okay, so first looking into Kw, which is also called the ionic product of water. So you need to know that water is very lightly dissociated. So if you're talking about a glass of water, it won't just have H2O in it, it will also have H plus and OH minus. So the water would have dissociated into that H plus and OH minus. See how both of them form a water molecule. But this is just in very tiny numbers. And so if you're talking about the Kc of that, so Kc, remember, is the constant of concentration, which we have looked at earlier. So you can see that, so the products would be at the top, so we have the H plus and OH minus at the top, and the reactant, which is the H2O, would be at the bottom. So what we can do is we can form a Kw. So what we can do is times the H2O, and that would get us Kc times H2O, which is also called Kw, and this is the ionic product of water. And the Kw at room temperature, which is 298 kelvins or 25 degrees, is 1 times 10 to the power of minus 14 moles squared and decimeters to the power of minus 6. And you need to know that the Kw, like Kc varies with temperature, Kw also varies with temperatures. So what this means is, if we were to increase the temperature of water, what tends to happen is more of the water would dissociate into H plus and OH minus. So we would end up getting a lot more H plus. So the pH of water could decrease. But we wouldn't necessarily call the water acidic now. This is because water is neutral if the concentration of H plus and OH minus is the same. So even if the pH was, for example, 2, and water could still be neutral if the concentration of OH minus is the same. So for every mole of barium hydroxide we will have twice the number of moles of OH minus, because it's BaOH2. So this also means that the concentration will be twice as big as the concentration of barium hydroxide. So we could say that the concentration of OH minus will be 0.2 times 2, which will just be 0.40. So now we could use the equation. So we could sub the values in. So we have for the Kw, we have 1 times 10 to the power of minus 14 is equal to H plus and OH minus, so we have 0.40. So then we could rearrange. So we would divide by 0.40, and we end up getting 2.5 times 10 to the power of minus 14. Alright, so you can be asked to work out the pH from a strong base that you're given. So for example, we've been given 0.20 moles per decimeter cubed of barium hydroxide. So in this, how we would approach this, so we're assuming that this reaction is occurring at the room temperature, so 298 kelvins. So we could use the Kw is equal to the H plus and OH minus. So we're using the ionic product of water. So we know that Kw at room temperature would be 1 times 10 to the power of minus 14. We do not know the H plus. This is what we're trying to find out. And the OH minus, so we've been given that the concentration of barium hydroxide is 0.20. So for every mole of barium hydroxide we will have twice the number of moles of OH minus, because it's BaOH2. So this also means that the concentration will be twice as big as the concentration of barium hydroxide. So we could say that the concentration of OH minus will be 0.2 times 2, which will just be 0.40. So now we could use the equation. So we could sub the values in. So we have for the Kw we have 1 times 10 to the power of minus 14 is equal to H plus and OH minus, so we have 0.40. So then we could rearrange. So we would divide by 0.40 and we end up getting 2.5 times 10 to the power of minus 14. Okay, so now the final step would be to minus log the concentration of H plus, which is 2.5 times 10 to the power of 10 times 10 to the power of minus 14, and that will get us the pH, which is 13.60. Remember to round this up to 2 decimal places. So now we can also be asked to find the concentration from the pH we've been given. So we've been given that the pH is 14.30. So now we can just find the concentration of the H plus by just simply doing 10 to the power of minus 14.30, which will get us to pH of 5.01 times 10 to the power of minus 15. And then now that's the H plus concentration, and then we can use the Kw value again. So it'd be Kw, so we're assuming this is at 25 degrees, so it'd be Kw is equal to H plus times by OH minus, and so we know that Kw is 1 times 10 to the power of minus 14 is equal to, so the H plus we've been given is 5.01 times 10 to the power of minus 15, and that will be times by OH minus. So then we could divide by OH, we could divide 1 times 10 to the power of minus 14 by 5.01 times 10 to the power of minus 15, which will get us the concentration 2.00, and that will be moles per decimeter cubed. Alright, so now we have been given a neutralization reaction, and we asked to work out the pH. And now for this particular reaction, we would have the base, the OH minus in excess. So first we would find the moles of the H plus and the OH minus. So looking at the moles of H2SO4 first, so that would just be 0.01, so 10 centimeters cubed. Remember to convert that into decimeters cubed. So 0.01 times 0.20, which will get us the concentration 2 times, the moles would be 2 times 10 to the power of minus 3. Now these are the moles of H2SO4, but we want the moles of H plus. So for every 1 mole of H2SO4, we would have 2 moles of H plus, because it's H2. So there would be 2 H's. So that means it'd be 2 times 10 to the power of minus 3 times 2, which is just simply 4 times 10 to the power of minus 3. Now we would find the moles of NaOH, which will be 0.015, so it's 15 centimeters cubed, times 0.30, which will get us the moles 4.5 times 10 to the power of minus 3. So now it's just NaOH, so the number of moles of OH minus would just simply be 4.5 times 10 to the power of minus 3. So by just simply comparing the values of H plus moles and the OH minus moles, I can see that OH minus would be in excess. So we would find how much OH minus would be in excess. So we would do 4.5 times 10 to the power of minus 3 minus 4 times 10 to the power of minus 3, and that would just be 5 times 10 to the power of minus 4 moles of OH minus in excess. So this OH minus in excess. So now we need to find the concentration of these OH minus, because remember, when we get the Kw equation, we can only simply put in concentrations. We can't put in moles. So we would find the concentration now. So the concentration of OH minus now. So we have 5 times. So we're looking at the OH minus in excess, because remember, so a lot of the H plus and OH minus would have reacted together. So this is only the leftover, which is in excess. So 5 times 10 to the power of minus 4. So then we would add the total volume. So it's 10 plus 15. So that's 25 centimeters cubed, which would be 0.025 decimeters cubed, and that would get us 0.02 moles per decimeters cubed, and this is the concentration of OH minus. So now we could use the Kw equation. So Kw again is equal to H plus times OH minus. So because this reaction's occurring at 25 degrees, we know that the Kw would be 1 times 10 to the power of minus 14. And then we have the OH minus concentration. So we do not know the H plus concentration, but we could use the 0.02, which is the OH minus concentration. We could find the H plus concentration by dividing by 0.02, which will get us 5 times 10 to the power of minus 3. So this will be the H plus concentration. And finally, we could minus log that to the power of to the base of 10, and that would be 5 times 10 to the power of minus 3, and that would get us the pH, which is 12.30 in this case. So just as a note, if you get in pH of less than 7, you know you've done something wrong, because we have the base in excess, so it should be above 7 as it's a base. Now looking at weak acids and weak bases. So you need to know that weak acids and weak bases only partially dissociate in aqueous solutions. So for example, if we had, so let's say this is our acid, this is our weak acid, and it will dissociate into H plus and X minus. Okay, so when we have a strong acid, what would happen is, for example, if we had 100 of HX, this would end up forming 100 H plus and 100 X minus. But for a weak acid, so we could be looking at ethanoic acid, not all of, so only a partial fraction would dissociate. So we could have, if we had 100 to start off with, what would happen when this dissociation occurs, we might end up forming 5 of them and 5 of them, so we would still be left with 95. So this is what's meant by they partially dissociate in aqueous solutions. And we could use Ka, which is a dissociation constant for a weak acids. Now it looks something like this, and this is basically exactly the same as Kc, but it's just Ka because it's just for weak acids. So we would have the concentrations of products on the top and a concentration of a reactant on the bottom. So in an exam, you can be asked, why don't we use Ka for a strong acid, for example? Now this is because all of the strong acid will dissociate. So what this means, if at the bottom we have the concentration of Ha, so what this means is if all of the acid dissociates, we can have 0 at the bottom, and you'll be breaking a math rule if you dividing by 0. So that's why we just don't tend to have a Ka for a strong acid. Okay, so we can get questions asking us to calculate the value of Ka, and what I would always do is I would approach this question by writing down the Ka equation down for that particular reaction. So I would say, like Ka, so it's always going to be equal to H plus and then the A minus. So in this case we're looking at ethanoic acid, so we would write down CH3 as C, then it would be OO, because we've removed that H plus, so it would be OO minus, and then it would just be ethanoic acid at the bottom. So remember, it's the products over the reactants. So this is our Ka, and we would normally get a mark just for writing this. And then we could find out the concentration of H plus. So you could just do 10 to the power of minus 4.65 because the pH is 4.65, and this would give us the concentration 2.24 times 10 to the power of minus 5. Now we've got the value for H plus and we have the value for CH3COOH concentration, so the ethanoic acid concentration, but we do not have the concentration for this, so CH3COO minus. So what you need to realize for this, so what I would write down now is that Ka is equal to H plus squared over the concentration of ethanoic acid. Now this is because, so if I were to write down, so looking at the dissociation equation, so if I had ethanoic acid and that's dissociating into H plus and the CH3COO minus. So what you need to realize for every ethanoic acid that dissociates, we end up getting one H plus and one CH3COO minus. So if we had 100 of ethanoic acid dissociating, we would have 100 of H plus and 100 of CH3COO minus. So we would have equal amounts of H plus and CH3COO minus. So that's why we can just write down squared as H plus squared. We don't need to find out the CH3COO minus concentration by doing something else. So the concentration of CH3COO minus would also be 2.24 times 10 to the power of minus 5. So then I can write down the other value. So by squaring this, I end up getting 5.012 times 10 to the power of minus 10. And then that's over 0.25, which is the concentration of the acid, and that will get that will get me the Ka value, which will be 2.00 times 10 to the power of minus 9. Okay, so now looking into pKa. So this is another logarithmic scale which is used usually to find out how strong a weak acid is. So we can find out pKa by simply doing minus log 10 Ka. So the same way we find out pH by doing minus log 10 of the H plus concentration, and we can get back to Ka if we have pKa by just doing 10 to the power of minus pKa. That would get us the Ka. So the smaller the pKa value is, the stronger the acid would be. So we can be asked to calculate the pH when we've been given the concentration of the acid and when we've been given the pKa. So what we can do in this question is find out the Ka value first. So again, we would do 10 to the power of minus 4.20, which will get us the Ka, and this is 6.31 times 10 to the power of minus 5. This is the Ka value. And then we can write down the Ka equation. So we can write down Ka. So if I don't know the formula of the acid, I can just write that it would just dissociate into H plus, and I can choose a letter I want. I'm just going to write A minus in this case, and I can just say it would be over H plus. Okay, so so I know the concentration is 0.150, and I have the Ka. So what I can then write is that I know that the the H plus value will be the same as A minus because the acid will dissociate equally. So I can just write H plus squared over HA. And then I can start to sub the values in. So this would be Ka, I know, is 6.31 times 10 to the power of minus 5 is equal to H plus squared over HA, which is 0.150. So I would get H plus squared to be equal to 9.465 times 10 to the power of minus 6. So this is when I would multiply by 0.150 to get H plus squared on its own, and then I would square root this, and I would get the concentration of H plus being 3.077 times 10 to the power of minus 3, and then I would minus log this value, and so this is to the base 10, and that would get me the pH, which is 2.51 to 2 decimal places.